Okay, thank you very much. Thanks for the invitation to be here. It's really great. This is my first trip to India, and I'm having a fantastic time, and it's been a great conference so far, so I'm looking forward to enjoying it, enjoying the rest of it. So I want to talk about hierarchically hyperbolic groups, but I think my lecture on hierarchically hyperbolic groups is really going to start tomorrow. So today, what I want to do is secretly it's about hierarchically hyperbolic groups, but it's about the motivating examples, so it's about mapping class groups. And so I'm going to go through and discuss what will be sort of background for the future talks, but in case everyone's not familiar with it, that's why I want to spend the whole day on this, motivating this example. So really, I guess the title of today's talk is Crash Course on the, maybe I'll double entendre, on the course geometry of the mapping class group. Okay, so this talk will be about the course geometry, about the large-scale geometry. So let me just say, so the standing hypothesis, just so I don't need to keep writing this, is I'll have a surface, which I'll just write off an S, but it will be a surface of a finite type. So SGP will be an orientable surface with genus G and P punctures. They'll both be finite numbers. They can be zero. Either can be zero. And then, just to remind you, the mapping class group of S is the group of homeomorphisms. Actually, maybe we'll take them to be orientation preserving. For what I'm going to say, it doesn't really matter, but that's often done. Orientation preserving homeomorphisms up to isotopy. Am I writing big enough? Is this visible in the back? It's a big room. I'll try and write a little bigger. Okay. So that's the mapping class group of a surface. And so the question is, how do we think about this? So this talk will have sort of a theme to it, maybe even a moral. So the theme is the following. The theme is that we can understand, we can try to understand the mapping class group via something that's a priori easier, right? This is sort of a group of homeomorphisms taken up to isotopy, and we can understand the mapping class group via just simple closed curves. Okay, so I want to sort of lay out some of the machinery for doing that, and then some of that machinery will get generalized in the future talks. So let's start with just a very simple example. This is an example that was what led Thurston to sort of his theory of mapping class groups, or it was certainly one of his motivators, so I'll call this Thurston's example. And let's take a simple surface. Let's let S be the four punctured sphere. So we'll just think of this as the plane minus 3 points. And here are 3 points. So I want to pick a particular element of the mapping class group and try to understand it. So here's one element of the mapping class group. I could take a homeomorphism that just that does a clockwise twist on these pair of elements. So I kind of put my fingers there, I move them, and then I let go, and I think of that as my element of the mapping class group. So there's one element of the mapping class group. There's another one I could get by twisting the other direction, B. Okay, so those are two different mapping class elements. So A and B are both in the mapping class group of S. And since it's a group, I can then compose them and get another element. So let's let phi be equal to, let's first apply A, and then let's apply B. Okay, so that's another element of the mapping class group. I just do one twist, and then I do this other sort of half twist. And then I try to understand what that element, so that's an element. This is some element phi. We'd like to try to understand something about that mapping class group element. So the way that we're going to try and do that is we're going to pick some curve Yeah, it's at infinity. So I'm not drawing it. I'm just drawing these 3 points in the plane. So what I can do is I can pick. Is the orange visible? I forget what Francois said. The yellow is not visible to him. So, okay. Can anyone see the orange that's there? Okay, good. Great. So I'm going to draw this orange curve. I'll give it a name. I'll call this gamma. And I want to see what applying this mapping class group element does to that curve gamma. And one way that we could keep track of what it does to that curve is, well, we can draw it, and I'll do that for a little while. But we could also kind of look at how this intersects some other curves. So let's draw some other lines. Let's kind of draw these 3 different lines here, and let's look at how often this curve gamma intersects that. So it intersects this first one 0 times, the second one once, and this third one once. Okay, so let's try and apply gamma now and see what we get. So to apply gamma, let's first apply A. Okay, so when we apply A, it takes this puncture and it pulls it over here and pulls this one over. So this loop that used to connect these two now looks something like that. Okay, and we could write down what these intersection numbers are. Maybe I'll write them in red. So now we get 1, 0, and 1. Okay, so that's not all of phi yet. That's just part of phi. To get phi, we now need to apply B. Okay, so what's B going to do? B doesn't do anything on this side. So this orange part, this little part over here of gamma stays the same, but this red part is going to get twisted like this, right? This loop is going to now go around here and then around this way. Okay, so this curve here, now what I've drawn, that was gamma. This is now phi of gamma. All right, and we could again write down these intersection numbers. We now get 1, 1, and 2. Okay, so we can't see much yet, but that's the first iteration. So let's try this one more time. So let's now go over here and let's apply A. Okay, so again we've got our 3 punctures. Now things are going to start to get a little more complicated. We're pulling this around. So we can see this loop here. That's now going to go over here, and when it does, it's going to take these 2 orange curves beside it, and it's going to push them out of the way. So it's going to go here. There were those 2 loops that we've now pushed out of the way, which now go around the middle puncture. And everything on the right side stays more or less the same. So on the right side, these 2 came here, they went around and came back. And we're not done with applying phi yet, right? We've only applied the first half of it, so now we can apply B. And so we want to pull this puncture over here and this one around. So this middle puncture now has 2 orange loops that come here and go out here. Where did this thing go? This got pulled underneath. So that came around here. This loop here stayed the same. Okay, and now we can kind of connect up this picture. Okay, we've drawn this slightly more complicated picture. Now this is phi squared of gamma. And let's write down, we were keeping track, we can do this counting here. We had 3 here, 1 here, and 2. And now we've got 3 intersections here, 2 intersections here, and 5 intersections. Okay, so the pictures, I have these 2 intermediate ones, but the pictures to focus on are gamma, phi of gamma, and now phi squared of gamma. All right, and as we do this, you can kind of, in your mind, start to keep track of what's going on. You can sort of see how I was pulling around and pushing these curves. So let me just skip ahead a step. Let's go straight to phi cubed of gamma and see what's going to happen. So when I do this, Or maybe I should do the intermediate step. Why not? Have 75 minutes. So what does the intermediate step do? But let's not draw everything. Let's just draw part of it. So the part of it that we want to draw is, so A is going to leave, right? When we apply A, everything happens over here. So the right side stays exactly where it was. Right? We don't change at all what's happening on this puncture. And so let's just draw these 5 strands that went around this right side of the puncture. Okay? And in the middle, what am I going to do? I'm going to take this middle one, I'm going to drag it here. So how many strands are going to go above here? Well, exactly the same number that I already had crossing here. So there's 3, I'm going to have 3 strands that go around here. Okay? So that's a start. And then what happens on the left side? Well, I'm going to take whatever strands are already here are going to, right? So whatever strands are already to the left of this puncture are going to stay there. So I'm going to pull this over here. So the number of strands that are over here, you can see is actually the number that's over here plus what I have in the middle. So let's draw this on the left. So on the left, we're going to get, let's see. So these curves are going to come from here. This one's going to get pulled around. So this is now going to go right down. Let's see if I can draw this in the right way. So let's just count how many we have here. We have, right, 1, 2, 3, 4, 5, 6, 7, 8. There's going to be, anyone counting from home. So we've got these 8 curves that are there. Those are all wrapping around here. And then this kind of pattern happens where these curves, just like over here, they flow around, they come along the bottom, and then some of them connect up to here, and some of them are wrapping around this way. So you can kind of, once you've drawn what's happened with these curves, you can just connect them up. And everything only matters up to isotopy, so the little wiggling that I drew doesn't really matter. And just to do one last application, B, so that we get another iterate of phi, we have these 3 curves. So I'm not going to draw everything, but let's just count what's going on. So actually, what was our counting here? So our count was, this was 8 here, this was 3 here, and this was 5. When we apply B, we're still going to keep these same 8 curves. We're still going to keep these same 8 curves on the left. And in the middle, right, on the middle, we're pulling this underneath. So above the middle curve, we're going to have whatever we had on the right. So there's going to be 5 that are going to loop around here. 3, 4, 5. So in the middle, we're going to get 5. Okay, so these are going to come down past that. And on the right side, we've pushed through what was here. So the number of curves on the right side is going to sum up, right? It's going to be this 3 plus whatever was crossing at the bottom, which is what we had over here. So we're going to get 13. 3 plus 5. So I'm not going to draw all of them, but we have these 13 curves here. Okay, so if you're enthusiastic, you can go home and kind of complete this picture, but let me just draw enough of it to convince you can get going. You take these paths, you just keep extending them. Some of these will start to match up on the right side. Okay, there will be some extras. Those extras will connect up here, and we'll get a picture. I haven't finished it yet, but that picture is very similar, right? If you're in the back, you may not even be able to tell the difference between these kind of large collection of lines. In this line here, this looks very similar to my picture of phi squared. So this is phi cubed of gamma. Okay, so sort of from a kind of boring your eyes point of view, that picture looks very similar to phi squared of gamma and to phi 1 of gamma. So there's already this kind of large scale picture of what's going on sort of remains this sort of converges to something very quickly. And what's it converging to? Well, if you look at these numbers, some of them may look familiar, right? These are sort of numbers from the Fibonacci sequence. So if you take the ratios of these intersection numbers, converge to the golden ratio. Okay, and you may think, well, I just started with some very particular curve, and so this is something that I was able to cook up for that reason. But in fact, if I had not taken the original curve gamma, but I took any curve in the four-punctured sphere, and I started iterating it, you'd get different intersection numbers, but their ratios would also converge to this golden ratio. So this is something kind of about this particular mapping class element. And so this kind of gives a picture of how you can start to maybe understand mapping class group elements in terms of simple closed curves. And so the goal of what I want to do today is talk about some other ways of I want to talk about some combinatorial structures associated with the collection of all simple closed curves on a surface, and then we'll use that combinatorial structure to get a handle on the mapping class group and its sort of large-scale group theoretic structure. Okay, so that's the plan. All right, so the next step. So let's kind of leave this concrete element behind for a few minutes, and let's talk about a combinatorial structure on the set of simple closed curves. Okay, so this combinatorial structure is going to have a name. So we'll call this the curve complex of a given surface S is going to be a simplicial complex. So let's just say is defined as follows. So it's a simplicial complex is defined by, I'll just tell you what the vertices, edges, and various simplices are. So the vertices of my complex are going to be in bijective correspondence with simple closed curves on S, by which I mean simple closed non-trivial non-peripheral, so not parallel to the boundary, non-peripheral curves on the surface S. Okay, so that's going to be my vertex set. And then my edges, I'll draw some pictures in a minute, but let's just put up the definition first. My edges, so when do I want to connect two simple closed curves, or the vertices corresponding to them by an edge? I want to do that if on the surface I can realize that pair of curves disjointly. Okay, so you put an edge if the pair, or if a pair, maybe between each pair, I can't speak English today either, I guess, between each pair of curves, which can be realized disjointly. Okay, so if on the surface you can homotope that pair of curves, if there's some representatives which are disjoint, then you connect them by an edge. And let me just say, I'm going to put a little asterisk here next to disjointly, and we'll come back and say what that asterisk is for in a few minutes. So those are what the edges are. And then you put an n simplex if you have a collection of n plus 1 curves which are realized disjointly. And I'll put the same asterisk there. Okay, so that's the abstract complex. So let's start with the simplest example. Pairwise disjoint. Well, so it turns out it's the same whether they're pairwise disjointly or setwise disjointly. It's a nice like sort of lemma in the geometry of surfaces that two curves can be realized disjointly if and only if there's geodesic representatives which can be realized disjointly in some hyperbolic metric, and then so you can then use that to prove the statement I just said. Okay, so you're right. So it was ambiguous the way I wrote it. You could think of this as pairwise disjointly or setwise disjointly, and they're equivalent. All right, so let's actually maybe before I do the example, let me just make one comment. So here's a remark. For almost everything I say, so often it is enough. So often we just consider the curve graph. So we throw away all the higher dimensional skeleton, the higher dimensional simplices. Consider the curve graph. Okay, so the one skeleton of this complex, and we define the whole curve complex because it's kind of, I think, intuitively it's useful to think about the full complex, but in practice, for most theorems that you want to prove, it's enough to think about the curve graph. So even if I say curve complex, it's often I'm thinking about the curve complex, but then working with the curve graph. Okay. Isotopy class of simple closed curve. Yes. Yes. Thank you. Isotopy class of simple closed. Thank you. Good. And it's a right. It's a lemma I don't want to say much about. Well, maybe it's a theorem I don't want to say much about. But it turns out that on surfaces, isotopy and homotopy are the same. So it's enough to. So I could say isotopy classes, or I could say homotopy classes of simple closed curves, and those will also mean equivalent things. So think about whichever one you prefer. Okay. So let's now do a. Should I go another board over? I don't know where the right threshold is for stopping. Okay, one more? All right. So, right, so let's start. So here's the simplest, interesting example. And it's going to be very simple for two reasons, and then one of those reasons we'll use, and the other reason we'll ignore. So let's consider S to be just the torus. So S10, so just the torus. All right? So for the torus, we have the nice property. So we know that the fundamental group of the torus, right, maybe I should be specific here, of the torus is isomorphic to its first homology, which is isomorphic to Z cross Z. Okay, so if I want to think about curves on the surface, the curves are parameterized by Z cross Z, and the closed curves, the closed curves are parameterized by Z cross Z, and the simple closed curves are the primitive elements in Z cross Z. So the primitive element, so the simple closed curves really correspond to rational numbers. They're parameterized by rational numbers, which roughly can just be thought of as you fix some basis. I want to make sure I get my parameterization right. So those taking notes. So let's think about it this way. Let's fix two curves, which I'll draw. I'm going to call this one 0, 1. Right. So that's just the rational number 0, but I'm going to write it that way. And let's draw. Is the blue visible also? Are both those colors visible? Okay. So I'll think of this curve as 1, 0. So those generate the first homology, and we can think about any primitive element as just the sort of the number of times it goes around one curve and goes around another. And you can check the primitive elements give you simple closed curves. Okay, so we know what all the vertices are. Okay, so the vertices are easy to identify. The edges are also easy to identify. What are the edges in this complex? To check who's awake after lunch. I felt like taking a nap because I had a ton of. You guys had my favorite vegetable for lunch. Is it Tindi? Is it? Okay. So I was very happy with lunch and I was ready to take a nap, but I'm here and I'm awake. So what are the edges? So there aren't any, right? Because every pair of simple closed curves, every pair of distinct simple closed curves on the torus intersect each other. So as defined, there are no edges. Okay, so that's not a terribly interesting complex. So what we want to do is, this is why we had this little asterisk here. So let's modify the definition slightly. Okay, so we modify what disjointly means to mean, right? So this is what my star asterisk was for. So instead of disjointly, well, let's just say, well, the minimum number of times that any pair of curves could intersect on the torus is once. So instead of saying disjointly, which would mean intersection number 0, let's just say, which would be intersection number 0, let's just say intersection number 1. So we say, instead of saying disjointly, we say intersect the minimal number possible on the surface, on S. Okay, I've broken to pieces the only piece of chalk that I can see that's white. There's lots of colors. Oh, here's another white piece. Great. Okay, so we modify the definition slightly. So we replace disjointly by intersect the minimal number possible on S. And that's going to be actually our new standing definition of what the curve complex should be in general. Okay, and now with that definition, things are more interesting. So now let's draw a picture. Okay, so we said we would parameterize the set of vertices by the rational numbers. So let's think of the rational numbers as kind of sitting on a circle. Okay, so there's my circle, and I wanted to put at the top of the circle infinity. Okay, so this is equal to 1 over 0. Okay, that's some vertex. Okay, and there's another vertex which I'll put down here, which maybe we'll think of as 0. Okay, and that's my 0 over 1. Okay, so those are two curves which I can't see from one side to the other. So one of those, the red one, which did I call red? I called red 0, 1. Oh, and I got to go back and get the red chalk. Okay. Just to keep track, let me just put the colors on here. So the red one was 0, 1. There's one vertex, and here's another vertex. Okay, maybe I'll just redraw the picture here for convenience also. So here's my red curve, and here's my blue curve. Okay, well, so I'm going to connect those by an edge. So this circle I've drawn is just for kind of psychological purposes, so I can draw a picture that's what I want. So think of this as sort of a dotted line. All right, well, once I've drawn those curves, it turns out that there's another curve which intersects both of those once, which I'll draw maybe in green. I haven't seen any green yet. Maybe that means it's not visible, but we could try and take this curve that goes around here and then twist around and comes back. So there's another homotopy class of curve which intersects the red curve once and the green one and the blue one once. So here's another curve, and let's think of that as 1, 1. Okay, and that's connected to both the blue curve. I'm going to draw this in a suggestive way with these kind of hyperbolic geodesics. So there's my green curve, and there's two edges connecting them, and this was 1, 1. Okay, and there's another curve which intersects that together with the red and the blue curve form a triangle, right? Which is the -1, 1 curve. So there's another curve which is over here, which is -1, 1. And actually, maybe this is a good time to mention. Here's a useful fact. So given two curves, which maybe I'll call PQ and MN on the torus, just given those numbers, you can figure out how many times they intersect. Okay, the intersection number, the minimal number of times these curves intersect, is just given by taking the absolute value of P, Q, of the matrix formed by putting the terms P, Q, M, and N and taking the absolute value of that. Okay, so you can check that in these things. It's just linear algebra. Once you've done it in these examples, extending that to all rational numbers is just a nice exercise. So this tells you intersection numbers, and now we can think about, sort of knowing that, we can easily write down some other curves which together with these ones we've drawn, form triangles. So for instance, I could add a vertex here. So it turns out that if I write the 2, 1 curve, you can check that that forms a triangle. Or down here, there's another curve, which is the 1/2 curve. Okay, and there's another curve, maybe I'll draw here. There's a 3, 1 curve, which together with 1, 0 and 2, 1. And I can actually do these quickly in my head because it turns out that there's a little trick, which is Fairy addition. If we have this P, Q, and M and N, and we take P plus M over Q plus N. Okay, so if you add fraction the way that, at least in the United States, most college students think you're supposed to add fractions, probably they know better here, but that's the way American students do it. If you do that, you get another curve. So this curve, this ratio together with PQ and M and N form a triangle. They form a triple of curves which pairwise intersect once. Okay, so we can keep completing this picture. There's a 4, 1 here, and it turns out that it's very symmetric. Okay, so you get this sort of beautiful picture, which is called the Fairy tessellation. So this is called, it's called the Fairy graph. Okay, and that Fairy graph is isomorphic then to the curve graph of S10. Okay, so this graph encodes sort of a combinatorial structure which encodes, it takes a set of simple closed curves and encodes in that there's sort of intersection patterns. One comma minus one is so let's see. So maybe I need to take this up to sign. So 1 comma minus 1 is the same as minus 1 comma 1. So it's the same projectively. So what? It's a slope, right? So what I mean, all I'm caring about is right. I mean, I have these curves, right? If I'm drawing them on the torus, right? I have a curve. I care about the slope of the curve. So thinking about 1 comma minus 1 and thinking about 1 comma 1, they determine the same slope, so they determine the same curve. Yeah, sorry for the small bad picture. Okay, is that clear? Okay. Okay, so now that I've drawn this curve complex in this one case, we can make some observations about this particular graph. So you can observe in this case, I guess if you believe the graph that I drew, then you get a complex which is finite dimensional. Okay, so it's you get a finite dimensional complex. Okay, that's one property. It's connected. Okay, so you can, given any curves which intersected a lot, you could sort of find this sequence of curves which each intersect the last one less time, and you could connect any pair of curves. So this is connected. Okay, similarly, you can realize kind of arbitrarily large intersection number, and so from the same picture, you also see that this is infinite diameter. Okay, so those are a couple properties you can see here sort of immediately in this simple case. Now, it turns out that all these properties generalize for arbitrary surfaces. Here's a list. So for general S, for that what? Well, yeah. So right, because you can't, because any edge is only decreasing the intersection number by 1, and so if you were at infinite, right? Okay, you're convinced. Good. Okay, so let me just say, so there's going to be a few exceptions to this, but in general, for general S, well, for S, except for some examples that will, except for the exceptions, which I'll note. So except for like 6 cases, the following is true. So C of S is a connected infinite diameter complex, which is locally infinite. Okay, that's actually a property that we could see over here too. I didn't mention it, but right, you can see at 0, there's infinitely many edges that come out of that single vertex, and the whole thing is symmetric. So every vertex, it turns out, is locally infinite, which is locally infinite, and has diameter and has dimension. So this is slightly different because that's one of the exceptional cases, but in general, it has dimension 3 times the genus plus the number of punctures minus 4. Okay, so let me say, maybe I'll first say what the exceptions are. So here are the exceptions. So there's the trivial exception. So if you take the closed sphere, there's no simple closed curves on there. So there's nothing you can do to make that an interesting, have an interesting curve complex. So this one, the curve complex is trivial. There's the once punctured disk, which also has no interesting curves on it, right? So that's also trivial. So there's S02. So there's the annulus. So it turns out, so the annulus also, right, every curve there is parallel to one of the 2 boundaries, or to both the boundaries. So this one also has a trivial curve complex. So this one we also won't think much about, although I'll make a caveat to that. And there's S03, which is the pair of pants. Maybe I should, if I'm going to call it the pair of pants, I should draw it like a pair of pants. Okay, so there's the pair of pants. That also, every curve on there is parallel to one of the boundary components. So there's no non-peripheral curves there. So these all have trivial curve complex. Okay, so that's why they're exceptions. And then there's a few exceptions, like the torus, where I needed to modify the definition a little. So those exceptions are ones that have curves, but every pair of curves intersect each other. So there's the torus, S10. There's the torus with 1 puncture. So on these pair of surfaces, there exist non-trivial curves, but every pair of curves intersect at least once. And so you've got to modify the definition so that instead of disjointly, you say once, and then this dimension bound will be slightly different. But modulo the dimension bound, the rest of these statements hold in these 2 cases. And then the one other exception is the 4-hole sphere. And in there, any pair of curves intersect twice. Any pair of curves intersect at least twice, so you need to modify the definition there also, and so you also get a different dimension bound, but everything everything else is true. So here you use the modified definition. Okay, and everything holds except you do get finite dimension, but you don't get the same dimension. You don't get this 3g plus p minus 3 dimension bound. Okay, so having said that, let's return to these kind of general properties and maybe just give a quick idea of why some of those hold. Some of them take more work, but some of them we can kind of quickly see. So 3g plus p minus 4. So let me say that now. So here's the dimension statement. So let's look at an example. So my favorite surface to think about is the closed genus 2 surface, because it already has lots of interesting phenomena happening, but it's simple enough that you can get a handle on things. So here, if we draw, as was just suggested, if we draw 3 curves, okay, then this triple of curves, if I remove them from the surface, it decomposes the surface into 2 disjoint surfaces, which are each pairs of pans. Okay, so it cuts the surface into 2 pairs of 3-hole spheres. Now, 3-hole spheres don't have any interesting curves on them, so there's no other curves that I could add. Okay, and so it turns out that this is a maximal collection of simple closed curves, and this number, right? This number of simple closed curves is so 3g plus p minus 3 is equal to the max. Maybe I should write it in white, it's more visible, is the max number of pairwise disjoint simple closed curves. Okay, well that was right. That was the way I defined that was the way I defined my cells, was to be some number of simple closed curves. Turns out this is the maximum number because this number forms a Pants decomposition. It forms a decomposition into 3-hole spheres, and so any other curve we throw in would reduce us to one of these other cases where we know that there's no more curves to add. So since this gives a Pants decomposition, this gives what's called a Pants decomposition. A decomposition into 3-hole spheres, we cannot add any more curves. Any more curves. Okay, so but the dimension of right, this cell has dimension 3g plus p minus 4 because it's a collection of 3g plus p minus 3 curves, right? You get 1 dimension less than the number of vertices. So this is our dimension, and it's useful because it already introduces this sort of thinking about these Pants decompositions, which turn out to be useful objects. One interesting thing about a Pants decomposition is I have these 3 disjoint curves. I can do something called sort of as an aside, right? So one interesting mapping class group element is a Dane twist, right? Where I just take my curve, I cut open along it, I twist by 360 degrees, and I glue back together. So that's a non-trivial element of the mapping class group. And if I have disjoint curves, it turns out that Dane twists commute with each other. So a Pants decomposition gives me a collection of 3g plus p minus 3 distinct curves that I can simultaneously kind of do commuting elements, that I can find commuting elements of the mapping class group for. So given a Pants decomposition, I can find an abelian subgroup of rank 3g plus p minus 3. So let me just say aside, so a Pants decompositions give z to the 3g plus p minus 3 subgroups of the mapping class group. Okay, and it turns out there's actually, we'll come back and we'll talk more about these subgroups later. These are sometimes called Dane twist flats. And the word flat, there's actually a geometric reason they're called flats, which we'll return to later. But there's these subgroups sitting inside the mapping class group. And there's a nice theorem from the early 80s of Berman, Lebowski, and McCarthy, which is that this is the maximal dimension of a free abelian subgroup of the mapping class group. So it's the maximal rank. Okay, so this dimension gives you, so you get this dimension bound from these Pants complexes, from thinking about these Pants decompositions. Another thing that we can see if we draw the genus 2 surface. So pick some curve, right? Maybe I'll draw this curve over here, this orange curve. Well, there's a lot of room in this surface. For instance, if I imagine taking, given that one curve, I want to show that I want to show this complex is locally infinite, and I need to show there's infinitely many other curves. Well, here's an infinite family. I could take a curve that goes around over here, and then I could find another curve where I twist once around here, or I could twist n times, so n twist. Those curves are all distinct homotopy class and simple class curves. They're all distinct from the single orange one. So this shows us that the complex is locally infinite. So this is the locally infinite part. Locally infinite. My time. Okay, so when do I stop? 3:15. Okay. Great. I'm on halfway through page 1. Right. So, actually, I'm slightly farther than that. Okay. So this is a locally infinite complex. All right. So some of the other properties take a little more work. Proving its infinite diameter takes a little bit more work. Connectivity is a nice exercise to think about. It turns out that the important fact is that, which is not that hard to prove, is that if you know the number of times that the curves intersect each other, the minimal number of intersections between those pairs of homotopy classes of curves, then the log of that number gives an upper bound on the distance in the curve complex. And so using that, you can kind of, the same way that I said on the torus, you could kind of reduce intersection number and show connectivity. You can also reduce intersection number and decrease and show connectivity for arbitrary surfaces. So showing it has infinite diameter takes some more work, and I'm not going to do that one. So those are some basic properties. Here's a non-trivial property. So this is a theorem of Mazur and Minsky from '99. So you could ask what happens. So we have this, this complex or GDS or graph, however we want to think about it. We could take kind of triples of points inside that graph, and we could look at, since it's a graph, a connected graph, there's some geodesic connecting any pair of points. And so given some triple of points in some arbitrary geodesic triangle, you could ask how that geodesic triangle, what it looks like. And so their theorem is that the curve complex is what's called delta hyperbolic. Okay, and so just to draw a picture of what that means, it means that if we take any pair of points A, B, and C, and we look at a geodesic triangle connecting them, there may be lots of different choices of what those geodesics look like, but any geodesic triangle connecting them, then the picture you get looks something like this. And something like this means, is very concretely, that there exists some constant delta, and if I pick two of these geodesics, so if I pick, say, AB union BC, then this will contain, so then the neighborhood of radius delta around this contains AC. So given any triple, then some pair of those, if you take the delta neighborhoods of that pair, it contains the third one. Okay, so that's what delta hyperbolicity means, and what they proved is that this complex has this very nice property, this very sort of strong geometric property, strong negative curvature property. And so a lot of what we're going to do is we're going to kind of make use of this negative curvature property of the curve complex. So the mapping class group, as I sort of said suggestively, I said explicitly it contains these large abelian subgroups. I called them flats. So that's sort of telling you that there's some zero curvature thing sitting inside there. But there's this very negatively curved space that gets associated to the mapping class group. And so a lot of the understanding of the large scale geometry involves kind of playing off between these flats and flat-like things in the mapping class group and the sort of negative curvature you get out of the curve complex. Okay, so let me now say what one of the tools is that we use to study the curve complex, or to get mapping class group information out of the curve complex. And it's called subsurface projections. It's a pretty simple idea, but there's a lot of mileage we can get out of it. So suppose that we're given some curve, suppose we're given some large surface, lots of genus, and some subsurface sitting inside it. So this is S. And then we have some subsurface. So S is the whole thing. And Y is some subsurface sitting inside it. So Y is an essential subsurface. So I want it to be, when I say subsurface, I'm always going to mean it's essential. So it's a pi1 injective subsurface sitting inside S. And so what we want to do is we want to take, turns out that there exists a map. So there exists a map which I'll call pi sub Y, which maps the curve complex of S to the curve complex of Y. So in the same way, for my surface, I defined a curve complex. Given any subsurface, well, that's also a surface in its own right, so you can associate a curve complex to that. And it turns out that there's a nice way that we can take curves in the ambient surface and project them down to get curves in the subsurface. And the way we do this is the following thing. It's what's called, it's intersection and surgery, okay? So it's gonna be intersection and then surgery. Okay, so let's take, we have some curve here. Let's see. Okay, so if I have some curve gamma sitting inside my surface, it maybe intersects this subsurface Y in lots of different ways, in lots of different arcs. Okay, so then what my projection is going to be is the following thing. So first, I'm going to just redraw my picture. So this is my intersection, which is just ignore everything but Y. Okay, so when I ignore everything but Y, I just get a pair of arcs. So intersection. So ignore everything but Y. Okay, this gives me some collection of arcs. And then what I'm going to do is I'm going to take parallel arcs, and I'm just going to pick one curve out of each sort of parallel class. So if they're kind of parallel modulo the boundary, then I'm gonna ignore one of them. Okay, so I'm going to take this picture, and then I'm going to just take one arc for each parallel class. In fact, I can just take one arc for each parallel class. Okay, and then this is an arc, not a curve. I want to get a curve, so now I do surgery. So what's the surgery? So I take my arc and I start following it along, starting at the boundary. I take an intersection point, I follow it until I get back to the boundary, and then I want to make it into a closed curve, so I just turn and I follow it around. And there was a choice there, right? I could have similarly followed it around and turned the other direction and gotten this. And I can look at, there may be several different choices I can do. And it turns out that at least one of them will be non-trivial. And there's different ways in which people study the subsurface projection. Sometimes what you do is you take all possible arcs, all possible surgeries and you look at that whole set of them, sometimes you just take one arc and you pick out one, and you pick one way of doing surgery so that you get something non-trivial. So I'm not going to show it, but there's a little argument that at least one of these will be non-trivial. And so I take one of the non-trivial curves, and now I've got my element in the curve complex of y. And it turns out that there was, if I made an arbitrary choice, then I may get a different vertex if I did something differently. And so the convenience of taking everything is then you know that it's canonical, but it's maybe more than a point. But it turns out that if you take all possible choices, you get a uniformly bounded diameter subset. In fact, you get a subset of the curve complex of y, which is diameter at most 3. And so from a coarse geometry point of view, it doesn't matter which choice you made. Let's write that as a little remark. So technically what I do is I don't get a map to the curve complex of y, I get a map to the power set of the curve complex of y, right? I get a subset of those curves, but it turns out that the subset of those curves I get is bounded diameter, so it doesn't matter which one I choose. Okay, so any possible choice of intersection arc and surgery can be done. The set of all possibilities has diameter less than or equal to 3. Okay, so that's a lemma that Maser and Minsky proved when they introduced these subsurface projections. It's not terribly hard, but it requires some kind of case enumeration to verify. But okay, so these things have bounded. So this is a projection. It's sort of well-defined, which sends points to bounded diameter sets, but uniformly bounded diameter. Okay, so let's move on from there. So from here, we can now get, so now what I want to do is I want to use this idea in order to build a model for the mapping class group. So maybe I'll move back to the left. So let's build a model for the mapping class group using simple closed curves. Okay, so instead of thinking of elements as being an element of homeo up to isotopy, this is going to be a simpler, or it's going to be a useful way to think about the mapping class group in terms of curves. Okay, so I'm going to say it kind of roughly, and you can ask me for a reference if you want to know exactly how we do this. But the idea is the following. So to start with, what we want to do is we want to pick a Pants decomposition of our surface. So choose gamma 1 up to gamma 3g plus p minus 3, which form a Pants decomposition. Okay, and what you'd like to say is, well, that almost already tells you everything that you want to know about the mapping class group. So if I fixed my favorite Pants decomposition, say it was this one, then I could apply a mapping class group element, and that would give me a new Pants decomposition, right? It will move this collection of curves to some new collection of curves, and I could try and use that, and I could ask myself, well, does that collection completely tell me which element of the mapping class I have, right? Could I just think about the orbit of what it does to these curves and read off which mapping class I have? And the answer is almost, okay? So the ambiguity comes from the fact that I could do these things that I mentioned before, which is Dane twist, right? So if I took a mapping class group and I sent this somewhere, and I did the same thing, but I did some extra twist on these red curves, I wouldn't be able to differentiate those just from looking at the image of the red curves, okay? So what I need to do is I need to augment this by adding some extra curves. So I want to take a curve which is going to allow me to record how much twisting I'm doing on each one of these red curves. So I'm just going to maybe draw some curves in here like this. So I'm going to add blue curves, which I'll call T1 up to T3G plus P minus 3. And these are going to record what I'll call transverse data. Okay, so actually here's a slight lie that I said before. Well, it's not quite a lie. So for the annulus, it's true that there's not an interesting mapping class group there. But it turns out that the reason that's a slight lie is that as a subsurface of an ambient surface, there is something interesting that can be told from annuli. So if I have a surface and I have an annulus sitting there, I can imagine how much a curve twists as it goes sort of around that annulus. And so in its own right, there's nothing I could say here. But if I'm thinking about this inside a surface, then I can think about the difference between a curve which cuts across it like this and a curve that winds around it many times. Okay, so those are two different curves, and so it turns out that there's a way that we can. So I don't want to go into the details, but there's a way that we can turn this into a well-defined. So I can think into an interesting curve complex. So we consider kind of all arcs connecting pairs of boundaries, modulo of the boundary, and we could think of them as being disjoint. Disjoint will need our star again. So if they intersect the minimal number of times, and then we could then build that into a complex. And when you build that into a complex, there's no canonical way to do that to get a complex which is exactly Z, but there's ways where you can build it where it's quasi-symmetric to Z. So sort of on a large scale, it looks like Z, or it looks like when Mladen talked about this in his talk the other day, he said it looked like R, right, which also looks like Z. So from a kind of large scale point of view, there's a nice complex there. And so there's a complex we can associate to an annulus. And so what we're going to do is we're going to think about these transverse data is going to record things in those annuli. Okay, so roughly what we want to do is we fix this base marking, you fix these transverse data, you apply your mapping class element to it, and then you kind of just read off where did it send the red curves and where did it send the blue curves. And from that collection of data, you can exactly recover your mapping class element. Okay, so roughly, you can determine the element of the mapping class group of S by fixing, once this is called a marking, by fixing one marking and then looking at its image. Okay, and you can turn these set of markings into a simplicial complex on its own right, and you can measure distance there. And it turns out that model that gives you a nice geometric model for the mapping class group. But from what we'll talk about in this talk, I want to just think about mapping class groups in terms of the orbit of this model, the orbit of one of these markings, because this allows us now, if we think about mapping class groups as what did it do to these curves, well, then that tells us that there's a nice way to, given any element of the mapping class group, to project to a curve complex. Because if I identify mapping class groups with markings, then to any mapping class group element, I can think of it being as being this collection of curves. And now, given any subsurface, I can take this curve. I can take I'll take the blue curves, the Pan-Seek opposition, and project it into the subsurface. So let me say that now a little more precisely. So by thinking of mapping class group elements as markings, we can define another map, which I'll abuse notation here and call it by the same name, pi sub y. But now, instead of just mapping the curve complex of S to the curve complex of y, I'm going to map the whole mapping class group of S into the curve complex of y. Okay, and we define this by we send, G, so pi y of G will be the following thing. So if let's say it like this. So if y is an annulus, if it's an annulus about one of these curves in the Panstick composition, about some gamma I, then I'm going to use the projection of to gamma I of the image of this transverse curve to I. Okay, so that's kind of the technical part that I don't want to talk about. But let's do the general case. So any other y, otherwise, let's ignore that case for a second. We'll just project to y. We'll just do the curve, right? Maybe for emphasis, I'll write curve of here. Project to the curve complex of y, the element g of my Panstick composition of gamma 1 union g of gamma 2 up to all of them, union g of gamma 3g plus p minus 3. Oh, two uses of the word g, but the idea is that this is now a simplex in the curve complex. So it's a bunch of disjoint curves. So it turns out if I project all of those, so at least one of those will intersect y because it's a Panstick composition. So they intersect every simple. Every simple closed curve will intersect that or be one of those curves, and then I just take those as curves and I project them down. So I kind of forget the rest of the mapping class group data. I forget all the transverse data. I just take those curves and I do what was my old curve complex projection. So maybe it would be better just in here write g of the Panstick composition. Okay, so I can take the whole collection of pants, right? And because the map as I defined it over here, it turns out is uniformly. It's I didn't say it. It's a uniformly Lipschitz map. So when I map in this diameter 1 subset, I still get a uniformly bounded diameter subset. No, well, we can define for each y we can define this. Yes. Yes. Yeah. So let me say it again. So here's my Panstick composition. In general, for almost every subsurface, you just take that Panstick composition, you look at its image under the map. That gives me some collection of curves, and I just project those using the curve complex projection to that subsurface. The one exceptional case is that if the annulus was an annulus about one of these curves, then it's hard to know what to do, and then I need to do something slightly different. Then I need to use this annulus projection, which I didn't really talk about anyways. So. What did you say? Yeah, so just like, okay, right. So again, I'm sort of thinking in this coarse point of view. So I'm projecting to this curve complex. I'm not getting a point. I'm getting a subset. But it turns out that this is also a uniformly bounded diameter subset. So we can define this and this map. So let me just say it. So here's a remark. Or maybe it's a lemma of Maser-Minsky, pi y. So the image of pi y is bounded diameter. Well, so pi y is a coarse Lipschitz map. Coarse Lipschitz map. Oh, I have 5 minutes left. Am I 5-minute warning? Okay, so this is a coarse Lipschitz map. So, okay, so let me just say, like, one special case of this is if y is the whole surface S, then this projection map throws away all the transverse data and just gives you the Panstick composition. Okay, so here's something that we could try to do. So we might want to. What's nice about these projections is that instead of working with this big space, we get a bunch of these spaces which are delta hyperbolic. So we want to try to encode the geometry of the mapping class group into those. So here's the theorem of Mazur and Minsky. Also from '99. Okay, so it turns out that the geometry of the mapping class group is totally encoded by these projections. So if I want to, so I'll put in the quantifiers in a second. Let me say roughly what the statement is. So, well, I'll put in one quantifier. For every pair of elements in the mapping class group of S, you can measure their distance in the mapping class group. Okay? And by distance, I mean the word distance, right? So it's just, which is well defined up to quasi-isometry. So any two word metrics give you quasi-isometric distances. Right? Quasi-isometric means that it changes distance by a uniformly bounded additive and multiplicative amount. So that's the best that we could ever tell is something that's up to uniformly bounded additive and multiplicative error. So this distance up to bounded additive and multiplicative error is given by the following thing. I could look at the distance in the curve complex of y between the projection to y of f and the projection to y of g. Okay, so for any y, I could do this. But then I could actually do this for every possible y at once. And so I could take all those projections and I could imagine summing them over all y contained or equal to S. Okay? And what their theorem says, lying slightly, is that up to uniformly bounded error, this sum gives you the distance, gives you the actual distance. So this is often called the quasi-distance formula or the distance formula in the mapping class group. Okay? And so the place where I'm obviously lying is that, right, for any pair of points, this is some number, some finite number, whereas this is now, there's infinitely many subsurfaces, this is an infinite sum. Okay? And so there's no way that this could possibly be true. I've got to be lying somewhere. But it turns out that I can make this true if I make this tiny little modification, which is, what does this mean? If I take some number and I threshold it at t, it means that if x is less than t, then I just throw that number away. Otherwise, I write down x. Okay? So I take these numbers, they may be infinitely many. Everything I said was sort of well-defined only up to something coarse, and so you expect there to be infinitely many of these that are non-zero, but it turns out that right, so now let me put in some quantifiers. For every, actually the quantifier should go up here. So for every sufficiently large enough capital T, there exist constants K and C. K is bigger than or equal to 1, C is bigger than or equal to 0, so that this is, so that by throwing away all the things that are less than T, you get KC kind of multiplicative and additive errors of how well this a priori looks like infinite sum estimates this distance over here. Okay, so distance in the mapping class group is encoded by kind of an infinite collection of distances in curve complex of y. And how close to my 5 minutes am I? 3 more minutes? Okay, so one thing that this almost looks like is it almost looks like, if you take the mapping class group of S, it almost looks like you have an embedding into this infinite product over y contained in S of the curve complex of y. And the reason that that's an almost is because this is not the L1 metric on that infinite product. It's some weird thing where I've kind of thrown away a bunch of small numbers. Okay, so this is not exactly the L1 metric, but it's roughly that. So this is sort of what's roughly true. And right, one of the things that Besvina's talking about in his lectures is a way of turning this into something that's true on the nose. You're not getting kind of a product of curve complexes, but there is some way of kind of converting this into something that gives you distance. Well, it gives you sort of better ways to. It gives you sort of a concrete way of thinking about this that's not kind of a quasi-distance, but an exact distance in some other space, but it's not just the direct product of the curve complexes. So having said that, in my last maybe 1 minute, let me just sort of advertise and sort of make a reference of how this connects to what Mohali was talking about in his lecture, which is now we have this map of the mapping class group into this infinite product of curve complexes. And so if I want to understand the mapping class group, it helps to understand what this image looks like. And so this is exactly, right? So given a pair of Y and Z, which are both subsets of S, let's strict subsets, so subsurfaces of S, then you can ask what the projection to Y cross the projection, what the image of this looks like. Ask what the image of this looks like. Right? So given the mapping class group, you're now sort of projecting into looks like as a subset of the curve complex of Y cross the curve complex of Z. Okay, so you take your mapping class group element, and now you're using this projection map, and you're projecting into C of Y cross C of Z. And so the two comments that I'll just make are if Y is disjoint from Z, okay, so if you have some big surface here and you have Y over here and Z over here, then the image of this can be anything, because I could take my arbitrary pair of pants over here and my, some arbitrary curves over here and arbitrary curves over here and complete that to a pants decomposition. And so the image is going to be kind of coarsely surjective at least. And so in this case, you don't get any control. But if Y and Z overlap, okay, which means that sort of one intersects the other, that they have non-trivial intersection and neither one's contained in the other, then you get this picture that he discussed last time, which is you have here C of Y and you have here C of Z. Then there's a natural point that gets picked out inside C of Y, and there's a natural point that gets picked out in here, and in fact the image looks like some neighborhood of this wedge of these two delta hyperbolic spaces. So this gets a long way towards trying to understand the mapping class group by kind of breaking things into understanding curve complexes, which are then delta hyperbolic spaces, which as Milan said, we sort of understand, although also sort of don't understand because they're complicated, and then understanding how pairs of those sort of fit together, and then trying to reconstruct the whole space out of that. So maybe this is now a good place to stop, and next time I'll kind of talk about some other another theory which kind of takes this as a model and then also connects this with what Mika Sagiv's been talking about curve complexes, and kind of finds a uniform language for talking about mapping class groups and curve complex and cube complexes and some other spaces also.